Okay, so we spent the first hour talking about gathering and organizing data. Let's take a look now at actually some calculating we can do. Putting data into the table or into a graph is a great way to organize it to make it quicker to see see parts of the information. But in order to communicate it quickly, it's often best to summarize it numerically. So when we're looking at summarizing data numerically, there are two things we're going to be looking at. One of them is we're going to be looking at measures of center and measures of spread. These have to do with what we call a distribution. The distribution is nothing more than a simple plot showing how the data falls over a range. For example, let's say that we have numbers that lie anywhere from 24 to 36 in our data. What we have then is basically a number line that we could number across here. 6, 7, 8, 9, 1, 2, 3, 4, 5. And let's say that whenever a number occurs, we put a dot above it. So if our value is 25, I'll put a dot there. Value of 30, 32, another 30, maybe a 35, another 32, a 30, 29. And as we add data points to this, this builds a definite shape to our distribution, assuming I evenly space them. But what if it's not just the integer values, 28, 29, 30? What if it could be 29.1 or 32.4? As those dots fill in, they actually form a shape, a solid shape that might look something like this. The highest point of that curve, which in this case would be right here, is the number that occurs the most often. So somewhere between 29 and 30 is the number that occurs the most. The lower points out here are numbers that don't occur nearly as often. So you could almost think of this as having an axis here where the frequency is labeled. The most frequent is the highest points on the curve. Every distribution is going to have a slightly different curve, but the most common curve is similar to the one we have here. What we've probably heard of is called the bell curve, because it's shaped somewhat like a bell. The official term for it in statistics is a normal curve. It's called a normal curve because that is the shape that data in nature normally takes. The height of people, if you were to get enough people and graph their heights, it would form a bell curve. Average daily temperature would form a bell curve. All sorts of things in nature would do that. So when we talk about measures of center, what we're looking at is where the center of this curve is. So I could have a number line here and have a curve that looks something like this. There's my bell curve. Its center would be located right here. I could have another curve that looks very similar to that one, but its center is in a different spot. So we need to find a numerical way of describing where that center is. I could have a curve, however, that has the same center. It looks something like this. This curve has the same center as the green curve, but it's much more spread out. So it has a different spread. So we're going to look at numerical ways of describing the spread or the width of that bell curve as well. So to help with that, I'm going to use, if I can, oh, maybe it won't let me. Nope, it's not going to work. Anyway, I've got a list of numbers here that I'm going to use for doing that. So this list of numbers here is just a set of 20 numbers that I randomly created. And we're going to take this list of numbers and we're going to look at finding numerical ways of finding the center and the spread of those numbers. So anyway, I'm going to do this to make it easier on me. So I can keep that set of numbers always where I can see it. We're just going to do this. Give me just a second to get this thing set to run. There we go. Okay. So one of the types of, where'd it go? Okay, sorry about that. So measures of center. There are actually several different measures of center. There are 3 main ones and a couple of smaller ones I'm going to talk about. One of the first main ones is something called the mean. The mean is the one that most people are probably familiar with, and that is really just what most of us have been talked about or have been taught as the average, the arithmetic average. To find the mean, you add them all up and divide by the number that are there. So some terms, some symbols that we're going to use. First of all, n is the number of items in the list. So in this case, we have 1, 2, 3, 4, 5. If we counted them up, there would be 20 items. So n equals 20 for this list. The symbol for adding things up, that is the sigma symbol. So sigma x means you're adding up all the numbers. So the mean is the sum of all those numbers divided by how many are there, or n. So for this list over here, if I'm going to add those up, I'm going to take 48 plus 61 plus 62 plus 73 plus 50 plus 69, oops, 69 plus 57, should have used a smaller list, 64, 48, 60, 59, 64. Now on your calculator, one thing I'll warn you is as you're adding these up, when you get to this point where you have them all entered, hit enter before you divide. Because remember, order of operations, what happens first, addition or division? Division. So we're going to divide by 20 because there's 20 of them here. But if we didn't hit equals or enter first, if we divide by 20, it's just going to divide the last number by 20 and then add it to the total of the rest of them, which would put us way off. So we have a total of 1,208. We're going to divide by 20. Gives us 60.4. So 1,208 divided by 20. 60.4 is the mean of this set of data. The second measure of center that's pretty common, the second most common, is the median. The median is physically the middle of the data. To find the median, the first thing we have to do is put the data, the numbers, in order from smallest to largest, which is not always as easy as it sounds. Looking at this list over here, finding the smallest, shoot, it changed on me. I shouldn't have done that. Anyway, it's a different list now, but finding the smallest number, there's 20 numbers there. That's not the easiest thing to do. I'm going to use technology to help me out a little bit here. First thing I'm going to do is make sure the numbers don't change on me again. Come on. The reason I've used a formula to create them so that if I don't so now it's just numbers. Before it was formulas in there, so every time I did anything with it, it was going to change the values. So what I'm going to do is I'm going to use Excel just to help me quickly sort these from smallest to largest. Then I got to put them in order, or put them in a row. One more out there. There it is. Okay. So I'm just going to sort these with my data filter, smallest to largest. Two numbers I got to be able to see yet. There, now I can see all 20 of them. So for my median, I now have those all put in order from smallest to largest. My junk out of my way. There. Next, I need to find the position of my median. So step one, put in order. Step two, find the position. To do that, I take n, which in this case is 20, times 1/2, or 0.5. So here n was 20, times 0.5 is 10. If this comes out to be a whole number like this with no decimal, that is telling me that the position of my median is between the 10th and the 11th number in my list. So coming over here, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th number is 66, the 11th number is 67. So to be between 66 and 67, I'm just going to add those two together. 66 plus 67 and divide by 2. Most of you probably saw that was going to be 66.5, but sometimes they're not right next to each other like that. So our median of that set of data is 66.5. That's the number that's exactly in the middle. Now I said that if this came out to be a whole number, it was between that position and the next one. What if it wasn't a whole number? So I'm going to put up a different set of data here quick. And for the sake of time, I'm just going to make a really small set, and I'm going to put them in order to begin with. So let's say I have 9, 12, 13, 15, 16, 21, and 27. For this set of data, what does n equal? 7. Very good. They're already in order, so that part is done. To find the position of my median, I'm going to take n times 0.5. So 7 times 0.5 gives me 3.5. Since that position is a decimal, we're going to round up. So that's telling us that the median is the number in the 4th position. So 1, 2, 3, 4. That would be the 15. You will notice that the median cuts the data in half. Half of the data is smaller than the median, half the data is larger than the median. Same over here. The median was right here. It cut the data in half. 10 numbers smaller, 10 numbers larger. So let's do some examples of just finding the position. So if n equals 17, what's the position of the median going to be? Well, 17 times 0.5 is 8.5. So what position would that be? 9th. We'd round up to the 9th. Perfect. If n equals 42, we'll take n of 42 times 0.5, which gives us 21. What position is that going to indicate? Since that is an integer with no fraction or decimal, it is between the 21st and the 22nd. What this is saying is there's 21 numbers before the median. So it's got to be between that one and the next one. This is saying there's 8.5 numbers before the median. So the next number in the list would be the center. We'll come back to that in a little bit. There's a third of our most common sets of, or most common measures of center, and that is the mode. The mode is strictly the one that occurs the most often. So looking over on this list, is there anything that's repeated more than once? Well, we have 51 that's repeated more than once. 51's twice. Let's see, 59 is 3 times. 67's twice. 69's twice. That's it. So 59 is 3 times. 59 would be the mode of this data. It is the number that occurs the most often. Now you can see the mode and the median are very different. We had the median of 66.5 and a mode of 59. The mode is not a very reliable measure of center. The argument usually comes down between the mean and the median to see which is the most reliable measure of center. Now most people would say the mean because it's satisfying. You added some numbers up and you divided, you cranked out a formula. It feels like you accomplished something. But let me show you an example here. Let's say that we have 7, 10, 12, 13, and 19. Let's find both the mean and the median of that set of numbers. Well, the mean is going to be found by adding them all up and dividing by what? There's 5 of them. So that is what? 61 divided by 5, 12.2 is my mean. The median is going to be found how? Well, first of all, they're already in order. That's step 1. What's step 2? Find the position. How do I find the position? Well, n is 5 times 0.5 is 2.5. That's telling me that the median is in what location? That rounds up to 3. It's in the 3rd position. The median is 12. So here the mean and the median are relatively close to the same number. That's good. That means this is a good set of data, good distribution. What if I add 1 data point to this? 50. Now the mean is going to be, well, adding 50 to that is going to be 111 divided by 6. $18.5. The median well, n is now 6, so it'd be 6 times 0.5 is going to be 3, which is telling us that the median is between the 3rd and the 4th. Because that came out to have no fraction or decimal, it's between that position and the next one. So between the 3rd and 4th is between 12 and 13, giving us a median. Averaging those two together of 12.5. So you can see here with that large number, the 50 put in there, the mean went from 12.2 all the way up to 18.5, a huge jump in the mean. The median, however, only went from 12 to 12.5. The median is much more stable for what we call outliers. That 50 was an unusual value. It's either way bigger or way smaller than the other numbers. So the median is generally considered a better measure of center because it is not as likely to be radically changed by those outliers. Let me give you a great example of this. In 1983, University of Houston advertised that the average starting salary for a graduate in their 4-year marketing program was just over $78,000 a year. Now, $78,000 a year would be really good money starting right now. I mean, extremely good money starting right now. To put it in perspective, in 1983, your average high school teacher was making about $16,000 or $17,000 a year starting. Great money, $78,000 a year. What they neglected to tell you was that one of the students who actually did graduate from the marketing program that year was a man by the name of Ralph Sampson. Mr. Sampson was 7'2", had been 2-time NCAA basketball player of the year, was drafted number 1 by the Houston Rockets in the NBA. Multi-million-dollar contract. It takes a lot of $20,000 a year graduates to average out a multi-million-dollar a year contract of $78,000. He was the only one in that group to make over $33,000 that year. The mean was legitimately $78,000. The median was $22,800. So there's an example where the median is a much better measure of center because it's not affected by that one radical value nearly as much. Like I said, in a good set of data without those major outliers, the mean and median should be approximately the same. There are other measures of center out there that we can look at that are used that are not as popular. One of them is something called the midrange. The midrange takes the smallest number, called the minimum. I can't write tonight. And the largest number, called the maximum. So in this set of data, the smallest number would be 51, largest would be 76, and it simply averages those two numbers together. 51 plus 76 divided by 2 is, what, 63.5, I believe? That's our mid-range. In a good set of data, that will be pretty close to the mean and the median. Relatively quick to calculate, but again, if you have an awkward set of data, it's not going to be near as close. So those are measures of center. Next, we want to look at measures of spread, how wide that bell curve is. The first thing, we've already talked about the mid-range. The range is a good measure of spread. Now, because the calculations for spread are a little more complex, I'm going to make up another small set of numbers to use for those calculations. So let's just have 13, 18, 21, 22, 24, and 31 is my set of numbers. So the range is nothing more than that largest number, which we call the maximum, minus that smaller number, which we call the minimum. So for this set of data, maximum of 31 minus a minimum of 13 gives us a range of 28. Pretty quick and simple. The problem is I can create another set of data with the same range with a much different spread. looking at this set of numbers here, even though they have exactly the same range, they both go from 13 up to 31, I would argue that the black line here is much more spread out than the green line, because these are pretty highly concentrated in the center there. So the range is not a great estimate of spread. It's quick, and it compared two sets that are radically different. But if they're close like this, if they have the same range, we need something more to distinguish between them. And what we generally use is something called the standard deviation. What the standard deviation does is it finds the average distance of each number from the mean of the data. Now I'm going to put the formula up here. Don't panic. It looks kind of complicated. We're going to break it down step by step. The standard deviation, S, is equal to the square root of the sum of each number minus the mean squared divided by n minus 1. Now something to note, this is the standard deviation for a sample. The formula, if it's a whole population, is slightly different. We never have the whole population to work with, so I'm not going to bother talking about the standard deviation for a whole population. So anyway, let's look at our first set of numbers up here. 13, 18, 21, 22, 24, and 31. The first step in again, I put the formula up here just to show it to you. We're going to do a step-by-step process. The first step in finding the standard deviation is to find the mean. So we're going to add these together. Of course, there's 6 of them. We're dividing by 6. What do we have there? 129 divided by 6, 21.5. Is that what you come up with for a mean? Somebody double check me. I don't trust myself at this point of the night. Good? Okay. So that's the first step. Step 2 is subtract the mean from each number. So I'm going to list the numbers out. I'm going to take my mean of 21.5 and subtract it from each of them. So 13 minus 21.5 is a negative 8.5. 18 minus 21.5 is a negative 3.5. 21 minus 21.5 is a negative 0.5. 22 minus 21.5 is a positive 0.5. 24 minus 21.5 is a positive 2.5. And 31 minus 21.5 is a positive 9.5. Now there's no reason to do it, but at this point, if you wanted to double check, if you're to add these up, they should add up to 0. Step 3. We're going to square each of these numbers. So negative 8.5 squared. First of all, you have to be careful. On your calculator, if you enter this incorrectly, it's going to try to tell you that this is a negative number, because your calculator is going to square it before it applies the negative. If I were to just type in negative 8.5 squared, it's going to try to tell me negative 72.25. That's not true. We know that any number squared is positive. A negative times a negative is positive. On your calculators, most of you have to enter it like this, with parentheses. So we get a positive 72.25. So a negative 3.5 squared is going to be a positive 12.25. Negative 0.5 squared, 0.25. Positive 0.5 squared is also 0.25. 2.5 squared, 6.25. And 9.5 squared comes out to be 90.25. Anybody need a second to catch up? Once we square each of those numbers, step 4 is to find the sum. In other words, add them all up. What do we have there? 84, 90, 180. Looks like 181.5. Again, somebody double check me just to make sure. Yeah, I'm pretty sure that's right. 181.5 is my sum. Step 5 is where it gets to be a little tricky. Step 5, we're going to divide by n minus 1. N, of course, is the number of items in the list. How many items are in this list? 6. N equals 6. That's why we divided by 6 in our mean. So if n equals 6, n minus 1 equals 5. So what we're going to divide by up here is 5, which is going to give us, is that 36.3? This number right here is not our standard deviation, but it does have a special name. That would be called the variance. So at the end of step 5, what we have found is considered to be the variance of the data. The standard deviation requires one more step. Step 6, square root. So the square root of 36.3 is 6.025. 6.02 we're going to round it to. That's our standard deviation. What that is saying is, on average, each of these numbers is about 6.02 units away from our mean. That's a lot to take in. I'm thinking maybe another example would be helpful just to get that process down. So I'm going to give you another list. So for this list here, what is step 1? Find the mean. So let's add these up. 3 plus 9 plus 11 plus 15 plus 22. We're going to divide by 5 because there's 5 of them. I get a mean of 12. What's step 2? Subtract the mean from each. So I have 3, 9, 11, 15, and 22. From each of those, I have to subtract my mean of 12. 3 minus 12 is a negative 9. 9 minus 12, negative 3. 11 minus 12, negative 1. 15 minus 12 is 3. That should have been 21, not a 12, or 22, not a 12. 22 minus 12 is 10. Now again, if I wanted to double check, what should this column add up to? 0. It would if you double check. What then is step 3? Square them. Very good. So negative 9 squared is 81. Negative 3 squared is 9. Negative 1 squared is 1. 3 squared is 9. And 10 squared is 100. What's step 4? Find the sum. Add them up, which is going to give us 200. Step 5. Perfect. Divide by n minus 1. What's n for this set? 5. So that means I'm going to divide by 4. 1 less than n. So 200 divided by 4 is 50. Now again, if we were looking for the variance, that would be the variance. To find the standard deviation, though, we still need to square root. Square root of 50 is 7.07. There is my standard deviation. What do you think? Easy to do? For this set of 5 numbers here, in your notes, I want you to find the mean, median, and standard deviation. Let's take a peek and see how you're doing so far. For the mean, what did you guys come up with? That's going to be brave. So 5 plus 11 plus 14 plus 17 plus 23 divided by 5, because there's 5 numbers there, which is what? 70 over 5 or 14, correct? Okay. For the median, they're already in order from smallest to largest, so that helps. Just need to find the position. N is 5, so 5 times 0.5 is 2.5. Since it's a decimal, we round up to the 3rd position. 1, 2, 3, that is 14. Relatively good set of data if the mean and the median are the same. Standard deviation. We've already found the mean for step 1. So step 2, we're going to subtract the mean from each. So we're going to subtract 14 from each of these. So negative 9, negative 3, 0, 3, and 9. Then we're going to square them. Negative 9 squared is 81. Negative 3 squared is 9. 0 squared is 0. 3 squared is 9. 9 squared is 81. Sum is 180. We're going to divide by 4. 5 minus 1 is 4. And divide by 4 is going to give us 45. And square root 45 You get 6.71. How many did 6.71 for your standard deviation? How many didn't quite get that far? Two of you? Okay. Any questions on how to get to the 6.71? Okay, well that is a good point in the night to take a break. So let's take our second break. We'll start lecture again at about 7:26.